welcome to this digital electronics tutorial class. So we will solve few problems on digital electronics, and this is with respect to the first year electrical science course. Let us see first the contents. We will cover the number system and discuss various type of number systems such as binary, decimal, octal, hexadecimal. And we'll see how these numbers are basically converted from one form to the another. Then we will do the binary arithmetic, that is addition and subtraction, and how these are being done for the binary numbers. We will see the 1s and 2s complement and do the subtraction and addition. The logic gates, we will see all the 7 type of gates such as AND, OR, NOT, NAND, NOR, XOR, and SNOR. And we will see the truth table for these particular logic gates. We will understand the Boolean algebra of all the laws, theorem, and their simplification technique to specific standard form SOP, that is sum of product and product of sum. And then the mean term and max term calculation we will see with the conversion method. At final, we will do the realization of the NAND and NOR gates, which are basically the universal gate implementation. So this tutorial is going to be lengthy. Along 144 problems will be there that we are going to solve it. So first we will begin with the overview of the number system. Common number system generally will have the binary, octal, decimal, and hexadecimal form. So these are basically on the particular basis. Like binary is having the base 2, which involve the digits involving 0 and 1. The octal number will have the base 8, and these involve the digits from 0 to 7. Decimal numbers are having the base 10, and we use the digit 0 to 9. Hexadecimal, which the base is being 16, here along with the digit 0 to 9, we are using the alphabet A to F. So A comes for 10 and F for 15. So we will see this, how these alphabets and numbers together are basically used for the hexadecimal number system. Now the question comes to the mind that why do we study the number system? In digital system, what we work is exclusively with the binary numbers, and we need to do the conversion between the different bases. That is very essential for the design of the digital system using the computer programming as well as the hardware interfacing. So although the number what we use in binary, this is basically obtained from the different other bases. So the key concept which lies is that any number with a base r, so r basically can be 2, 8, 10 and 16, can be represented in this particular form. So n is my number which can be obtained when the number is having any base in from 2 to 16. So here we can represent that. So here we are using r raised to the power 0 to r to the power n. So we are moving from left to right in the order of the 0 to n power of the number bases. We will see how to obtain this one. So let us see the first problem. The first problem where we will use the decimal to binary conversion, and the problem asks us to convert the decimal number. So the decimal number that we have is basically 156, and here the subscript 10 indicate that this is in decimal, which we need to convert into binary form. So binary form means the base will have 2. So how do we do that? So let's see the solution. So we take the number 156 and we do repeated division by 2. So let us start with 156. We divide with 2, so we get the quotient as 78 and the remainder as 0. So this process of division, then we move to 78 divided by 2, we got the quotient 39 and the remainder is basically 0. Then we take the number 39 and keep on dividing this number until the last, and we obtain the remainder. So this remainder what we see is basically taken from the last, which is the MSB. MSB stands for most significant bit, and we have the LSB, which is the least significant bit. We take this number in this form and this will be our final answer. So the number 156, which is basically the decimal number, it is being represented as the binary number written in this form with the base 2. We can cross validate whether this simplification process is correct or not using conversion of this number in the decimal system. So here if we see, this is the position of 0, this is the position of 1, and so on. So we can do and multiply 0 into 2 to the power 0 plus 0 into 2 to the power 1 dot dot dot. We will get these numbers in the decimal system, which comes to be 156. So that indicates that whatever calculation we have done, that is correct. Problem number 2, where we have the decimal number and now we need to convert to octal. So the number that we have taken is 237, and this is in decimal format, so it is in 10 base, and we need to obtain octal conversion, which is in base 8. So again, similar to the previous problem, here we will do repeated division by 8 instead of 2. So we divide the first 237 with 8, we get the quotient as 29 and the remainder as 5. So this is our least significant digit, and the same process we continue in zigzag. So our last or the most significant digit is 3, and we go from the reverse order. So we get the answer to be 355. So it means that 237 in decimal 10 is basically equal to 355 in the octal system. Now this number again we can cross validate with our verification process, where this is the position of 0, this is 1 and 2. So we have 5 into 8 to the power 0 corresponding to this one, and then we have 5 into 8 to the power 1 and 3 into 8 to the power 2. So the octal system 8 is now converted to the decimal system 10 with the value as 237. So which matches with our question. So it is correct. Problem number 3, where we have the decimal to hexadecimal conversion. So the number that we have taken is 2890, and this is in a decimal, so base is 10. We need to convert to hexadecimal, which is 16. So we will do the repeated division by 16 now, not with 2 or 8. So the number we have taken 2890, this is divided with 16, we get the quotient as 180 and we get the remainder as 10. Now remember, we have seen that in the hexadecimal system we are using the number 0 to 9, and then we are moving to A to F. So here A will be taken as 10 and F is taken as 15. So here, since we got the remainder as 10, which is equivalent to A, then this number 180 is again divided with 16, we get the quotient as 11, remainder as 4. Then 11 is again divided with 16, we get the quotient as 0 and the remainder is 11. So 11 means B in the hexadecimal system. Now we are moving from the MSB to LSB, that is the digits. Then we are having the answer as B4A, which is in the base of hexadecimal. So if we want to cross validate this, the position here is 0, 1 and 2. So this one will be having 16 into 10 to the power 0. Then we have 4 into 10 to the power 1 and 11 into 10 to the power 16 to the power 2. So what we get is 2890, which matches with our answer. So we can cross validate similarly with other systems also. Problem number 4, where we have the binary number which is in base 2 and we need to convert to decimal. So here the number we have taken with the digits 0 and 1. So we can see here this number can be converted to decimal by multiplying each bit by its positional weight and sum. So here the position starts with 0, then we have 1, 2 and so on. So the last one, if you see, it is a 0, so and it will be having 0 into 10 to the power 0 and 1 into 10 to the power 4. So this is, we will start like this, and if we add it, this whole number, we will get 214. So it means that the decimal number, this one, is basically equal to 214 in the decimal system. So the binary number system is converted to the decimal number system, which is 214. Now we take the octal, which is 742, and we want to convert into decimal. So we do the same process here. 742 we have taken. Now the position what we have is 0, 1 and 2. So here we multiply this number 2 with 8 into to the raised to the power 0, 4 into 8 to the power 1 and 7 into 8 to the power 2. So this comes to 482, which is our answer in the decimal system. We'll do hexadecimal to decimal conversion, and we have taken the number 2A, 5, F15, and we have to remember from A, B, C to F how these numbers are represented in the hexadecimal system. So the position, let us see, this one is 0, 1, 2 and 3. So F, which is indicator of 15, so we are getting 15 into 16 to the power 0. Next we have 5, so 5 into 16 to the power 1 and so on till 2. So if we add this one, we get 10847. So this is our answer in the decimal, and we have done the hexadecimal to decimal conversion. Problem number 7, where we have the binary number and this number has to be converted to hexadecimal. So how to do that? So let us see the method. So this there we have lot of bits are there. We need to group this bit in set of 4 from right to left. But if you go from right to left, we will not understand what is here we have. So what we do is that we group from here 1101. So this is 4 bit. Then we have 1, 2, 3, 4. Here we have 4 bit. Then we have this one as the 4 bit. So this way we have grouping. Now see here what is happening. This we have 2 bits only. So it means that we can add 0 at the beginning to make this padding with 0 to complete the 4-bit system. So that is what we are doing. So the binary grouping that we have done with the 4 set of bits, and we have paired with 2 zeros in the beginning, and the corresponding number that we get for this 4 bit is we can obtain it, and the answer that we will be getting is 2DCD in the hexadecimal system. So for quick reference, each hexadecimal digit represent exactly the 4 binary digits with what we have. So this is the process of conversion of binary to hexadecimal. Next, we have the binary to octal conversion. Now here we have the base as 2. We are going to convert to octal. So we will be having the set of 3 now in this case. So we can make the digit group in the set of 3. So when we do the set of 3, we get this numbers, and then the equivalent octal digits we can obtain, which is 7, 6 and 5, and the answer comes to be 567 in the base 8, which is the octal. We can cross validate this one with the conversion from octal to the binary number, which is 375 we get, and the same number what we got in binary, if we want to convert in the decimal point, we get 375, which is again the cross validation is correct. Next, we have the hexadecimal to binary conversion. So we have the number 3A5F, which is in hexadecimal. We are all going to obtain the binary. So we need to group the hex digit with 4 binary digits. So when we group it with 4 binary digit, then what we get is that 3A5, its corresponding equivalent binary what we have, then these numbers we are going to represent here in the final form. So we get the hexadecimal to binary, and we do the verification converting from hexadecimal to the decimal system. We get 943, which is again can be validated from binary to decimal number system. So 943 what we have in the decimal number system is basically equivalent to 3AF in the hexadecimal system. Next problem, where we have the octal to hexadecimal conversion. So here the number is 725, which is in the octal system 8. We want to convert to hexadecimal system. So there are basically 2 steps process. So we want to convert this through binary, which is the intermediate step. So first we need to convert the octal to binary and then move to binary to hexadecimal. So this number 725, that is in octal system, let us go to the binary, and each octal digit will have 3 bits. So 725 in octal, we will have 3 bits in the binary system. Now we got this one as basically in the binary system. Now again, we use this binary number system and group with 4 digit to convert into hexadecimal. So our final answer will be 1D5 to the base 16. So whenever we need to convert octal to hexadecimal, usually we follow the process going through the binary as the intermediate step. Now let us do the addition and subtraction for the binary numbers. So we take the two numbers a and b. This can be more also, and we form the numbers with different possibilities 0 0 0 1 1 0 and 1 1. If we add these two numbers, then what we get? So 0 0 will be having the sum as 0 with the carry 0. 0 1 is having the sum 1 with carry 0. 1 0 will have the sum 1 with carry 0. 1 1 will have the sum 0 with the carry 1. So here you can see this particular number in general, which is 1 plus 1 means both are high. The sum is basically 0 and the carry is basically 1. So this process of carrying addition can be done for more than 2 bits also. So if you have 3 bit or 4 bit, then also we can do it properly with having this the sum and the carry process. So here we can see we have taken example of 3-bit system and how do we convert this into different addition. So let us do the problem number 11, where we have the simple binary addition. So we are going to add these two numbers which are in the binary number system, and if you observe these two numbers, we have so many bits we have. So let us see the addition. So here we see, so we have taken the first number 1011 and the second number which is 1110 that we have taken. Now we are going to add 1 plus 0, which is giving me 1 and the carry is 0. 1 plus 1 is 10, which is having 0 as the sum and 1 as the carry. 0 plus 1, we have the 0 and the carry is 1. 1 plus 1, now here we are going to add with this one as the carry whatever we have. So finally we will have the representation 1 1 0 0 1 1. So this step by step what we is shown here, where we are adding the numbers and we are finding what is the carry that we have. So whatever the carry is there, then that is being added to the next bit and we get the answer. So what is the answer that we have? It is 1 1 0 0 1 to the base 2. We can do this verification process by converting this binary number into decimal and the second binary number into decimal. So the first one is basically 11 and the second one is 14. So if we add 11 plus 14, that is again coming to be 25. So there is a validation that yes, in whatever we are doing in the binary number system, the same we are getting in the decimal number system. Now, if we have multi-bit binary addition, so many bits are there and then we are adding it. So the same process we are going to do, whatever the example we have taken earlier. So here we have the first binary number 10110101, which is what we have written here. The second one we are writing it here, and then we are adding this number 1 plus 1 is 10. So we are getting the sum 0 with the carry 1. This 1 is basically added with the second one, so that is basically 0, and then we will have the carry. So this process is going to be repeated and we will represent this one. Again, the validation can be possible by taking this number and the second number, converting that into its corresponding decimal number system to find what is the actual sum that we have. So in the decimal number system, we are having 400 as basically the value of this one. Now we will do the multiplication. So binary multiplication is simpler than the decimal process. So here we have two binary numbers a and b. We are going to multiply that. So 0 cross 0 is 0, 0 cross 1 is 0, 1 cross 0 is 0, except the number here which is 1 cross 1, which is 1, all will be having 0. So anywhere where 0 is appearing, it will come to be 0. So the process is multiply each bit of multicand by each bit of the multiplier and shift the partial product appropriately and add all the partial products. So this process we are going to see in some example. So let us take the first example where we are going to multiply the two binary numbers. So the first binary number is 1101 and second one is 101. We are going to do the multiplication. So first we are going to multiply this 1 cross 1. So multiply with 1 all the numbers. So we get 1101. Then we are going to shift this with 1 digit and then we take the second one, that is 0, we are going to multiply, then similar process we are going to shift 2 times, and then we do the multiplication. And the final, we are representing the addition of these 3 steps, which comes to be our answer. And the verification says that this is equivalent to the 65 in the decimal number system. Again, if we have large binary numbers that we have and do the multiplication, so again the process remains the same, where we can have multiple shifting that we have in the steps where we have the multiplication. So if the binary numbers are large, we have to shift multiple times, but the process remains the same. Again, we have to add it and represent the final answer. So we can also validate this by converting the binary to the decimal number system and finding what is the answer for this one.